In the transonic range, the airflow around the aircraft is mixed. Part subsonic, part supersonic. The dark green represents regions of subsonic flow. The light green, supersonic. Shock waves are shown in red. This film is about the supersonic range, where the main flow everywhere is supersonic, shown as before in light green. To understand supersonic flight, it is necessary to examine the nature of supersonic airflow, which behaves more simply than subsonic. First, consider what happens when a single point is moving supersonically. The pressure waves sent out continuously at the speed of sound form a round cone, the Mach cone. The lines forming it are called Mach lines. The half angle of the cone is called the Mach angle, usually shown by the Greek letter mu. The size of this angle depends on the ratio of the point's forward speed to the speed of sound, that is, on the Mach number. At Mach 1, the Mach angle is 90 degrees. As the Mach number is increased, so the Mach angle grows smaller. A similar effect can be seen by dipping the point of a pencil in a fast-moving stream of water. Only the region inside the wave is influenced by the pencil point. The water outside this region flows on as if no disturbance existed. In the same way, the supersonic point can only affect the air lying inside the Mach lines, shown here in white. Ahead of the Mach lines, the air is undisturbed. Since all the disturbances coming from the point are infinitely small, the speed and direction of the airflow, shown here by white streamlines, don't change as the air passes through the Mach lines. But what if the disturbance is large? Such a disturbance is produced by a leading edge in supersonic flow. An oblique shock, the bow wave, is formed. How does the flow behave as it passes through such a shock wave? Consider first the diagram of a normal shock wave. This, at right angles to the flow, always slows it down from supersonic to subsonic. The speed is represented by the length of the arrow. Here is an analogy. This toy animal walks down a sloping board, faster down the steeper part, and then slower. Here's the same thing seen from directly above. Supersonic, subsonic. If the whole board is now pushed sideways, the animal's path across the screen is a straight line which bends suddenly. In just the same way, imagine a uniform sideways velocity superimposed on the airflow. This will not be affected by the shock wave and will be the same on both sides of it. The resultant airflow is now like this, exactly as it was for the animal. It's now supersonic past the shock wave, but slower than ahead of it. If now the whole picture is turned around so nothing is changed, the shock wave is oblique to the airflow and has deflected it and slowed it down. Pressure always increases when velocity is lower. And if streamlines are drawn, they are closer together past the shock wave than ahead of it. The shock wave can be caused by a solid surface with a sharp corner. The streamlines are parallel to the surface. The surface may be the leading edge of a wing. This deflects the flow in exactly the same way. This supersonic wing section has another kind of sharp corner. Here, just the reverse happens. The streamlines move further apart. The speed increases. The pressure falls. After turning the corner, the streamlines are parallel to the new surface. This is called an expansion. How does it happen? Consider a streamline very close to the surface. The influence of the sharp corner will be felt along a Mach line at the appropriate Mach angle, just as the influence of the pencil point is confined to the region bounded by the Mach lines. None of the streamlines will be affected until they reach this Mach line. As soon as they pass it, they bend slightly and move further apart. The influence of the corner is at once felt along a new Mach line, and the streamlines bend again, and so on. An expansion at a corner can be looked on as a series of tiny changes in direction, pressure, and speed. The expansion ends at the Mach angle corresponding to the final speed and direction of the flow. So it is confined to a fan-shaped region between the first and last Mach lines. Inside this region, pressure, direction, and speed change smoothly, unlike the shock wave case, where there's a sudden change in direction and pressure. But in both cases, supersonic flow wheels around to follow the new surface with little disturbance. Here it is obstructed and so slows down, while here it's being helped on its way, so it speeds up. Compare the behavior of subsonic flow around a similar corner, shown here in a smoke tunnel. The airflow slows down suddenly, and the pressure increases. The boundary layer separates and breaks down the streamline flow, so sharp corners like this are avoided on subsonic aircraft. Supersonic flow behaves much more smoothly and simply. Boundary layer separation is relatively unimportant. How do these facts about supersonic flow affect the design of actual aircraft? Here's a wing section which would give lift at supersonic speeds. A thin, flat plate. Here is the flow pattern. On the upper surface, the pressure is less than atmospheric, so there's an expansion at the leading edge and a shock wave at the trailing edge. On the lower surface, the opposite happens, and the pressure is greater than atmospheric. Here is the pressure distribution. This area is a measure of the lift. The center of lift is at the midpoint of the wing. Unfortunately, a wing like this is not practical structurally. Here's one answer: the double wedge. The thickness here is exaggerated.